Washington State University. Go Cougs!
Hello and welcome to the course on statistical inference. In the first module, we'll be giving an introduction to statistical inference. And in the first part of this module, we'll be looking at some definitions and the different types of data and methods involved. Our definition of statistical inference for this course will be a process for discovering trends based on the analysis of a sample of data taken from a behavior of interest. We've seen in another course where we have collected sensor data from users, and so we may want to, for example, look for a linear relationship between the different sensor values, in this case between two different acceleration dimensions. Or we may want to cluster the data to see if there are some strong categories that the data falls into. So these are examples of statistical inference. To do a more detailed example, let's take a look at some specific questions we might want to ask. To start with, let's recall if you took the separate course on collecting smartphone sensor data. In that course, we collected data from the accelerometer, which gives acceleration in the X, Y, and Z direction. And we also collected gyroscope data, which gives us the attitude of the device as a yaw, pitch, and roll value, and also the rate of rotation about the X, Y, and Z axis. So in a separate experiment, I collected some sensor data from these sensors, and I collected them while doing two different activities, work and play. And so you can see here the data values that were collected, the first few for the activity work and the last few for the activity play. In all, we have 56 examples of this data, and that data set is available as part of this course. Now, what are some questions that we may want to ask as part of statistical inference? One question may be just whether we see some general trends in the data. So here I've plotted the accelerometer values along the X, Y, and Z axes in a three-dimensional plot, and the points for the activity work are colored in red, and for activity play are colored in blue. And so here we can see that the points for the work activity are pretty closely clustered together here, whereas the points for play are a little bit further away from that tight clustering. In fact, there are several points for the play activity that are off this particular plot range. So at this point, at least, we can see some general trends in the data. We might also want to see if we can learn to predict what activity the user is doing based on their accelerometer data. So one way of doing that is to try to learn a decision tree that asks questions about the different values of the sensors and then concludes a prediction of to what activity they're doing. So in this particular decision tree, the first question we ask is whether the acceleration in the Z direction is less than 0.0008. If it is, we go down the left branch. If it's not, then we go down the right branch. And eventually, by asking these questions, we'll get down to these leaf nodes where we will then make a prediction. So in this first leaf node, we see that a total of 10 of our original 56 examples, 10 of them came down to this leaf node. And since a majority of them are of the activity play, then that is the prediction that it would make. But of course, it would make two mistakes because two of the work examples would also come down this path. In these other leaf nodes, we see similar behavior. So here, examples that come down to this leaf node would also be categorized as play. In this case, 14 examples came to this node, and all 14 of them were classified as play. In the next one, we see 25 examples came down this path through the tree, of which 24 of them have activity work, and so that is the class that is predicted. But of course, it makes a mistake on one of the examples. And finally, this leaf node, 7 examples came down this route, all of which are activity play, and so play is the activity that's predicted. So if we were using this tree to classify the 56 examples that are in our data set, we would get 53 of the 56 correct for a general accuracy value of 95%, which is a pretty good result for predicting whether someone is working or playing based on their accelerometer data. So these are the kind of questions and methods and models that we can apply in order to perform statistical inference. Now let's step back a little bit and talk a little bit more about the types of data that we might see. We've already seen that the data is generally divided up into features and classes. So here's again a spreadsheet of some of the data we've collected, and we have these 9 features for yaw, pitch, roll, rotation, and acceleration. And then we have our class value, or the activity that the user was performing. So within the features, we generally see 2 different types of features. We have numeric features, which are obviously numbers, sometimes also referred to as continuous or real or integer. And we also have categorical features, similar to activity here, but other such features, for example, color, they have specific values that aren't necessarily ordered or numeric. These are also sometimes called nominal or discrete features. And then usually for the data, there is a class that we're trying to predict. In this course, we're mainly going to be focusing on predicting the user's activity based on their sensor data. And again, the class can be either a numeric or a categorical value. If we were trying to predict a numeric class, for example, predict the user's weight, when you're predicting a numeric value, you usually call that a regression problem. Whereas if you are trying to predict a categorical value, for example, in our case, one of several activities, then that is typically called a classification problem. So those are the types of data that we'll see among the features and classes that make up our data. Now the types of methods that we generally apply to this data, we've already talked about classification and regression, and we saw an example of a decision tree that did classification in terms of predicting the activity from sensor data. We might also want to perform a clustering, and we saw an example of that where we're looking for, again, the strong subsets that are subsets of points that are similar to each other but dissimilar from other subsets of points. Now, in the data that we have, you see that we have, it's basically 9 dimensions, 9 different values, but it's possible that we could get data that has many more dimensions. We may, for example, collect compass headings and GPS locations and environmental information and other sensors that are available. So our data can get very high dimensional, and that typically makes the statistical inference more difficult. And so one approach to that is to try to reduce those dimensions down, and we'll look at some techniques for doing dimensionality reduction. One of which you may have heard of is a fairly popular approach called principal components analysis, which basically projects a high dimensional problem down to a few small dimensions. And finally, we want to be able to evaluate these various models that we're learning. We saw how our decision tree achieved a 95% accuracy rate. And accuracy is one major metric that we will compute for our models. But there are some other techniques for getting a better idea of how good our models are going to perform and also comparing two models to determine which one is superior. Finally, we also want to look at some tools for performing statistical inference, and there are several good tools available for us to work with, and I've listed 3 of them here. R is a self-contained package that uses its own language, the R language, and it has several statistical inference methods built in, along with some visualization tools for visualizing the results. Weka is another tool suite for doing statistical inference, and it's written in Java, and it also has a nice user interface and several visualization tools built in to look at the models and evaluate them. The third, and probably the most popular right now, is the scikit-learn toolkit, which is written in Python. And while it doesn't specifically have visualization built in, it can use various other visualization packages, a popular one being the matplotlib library, which we will be using in this course. So we will be focusing on the scikit-learn package in doing the statistical inference. So in the next part, in part 2, we'll be taking a closer look at this scikit-learn package and doing a few examples.